This is problem 11-22E. It's on page 632. Figure P1122 shows the proposed design for a hydraulic press used to compact solid waste. A piston at the right is capable of exerting a force of 12,500 pounds through the connecting rod to the ram. The rod is straight and centrally loaded. It is made from AISI 1040 WQT 1100 steel. WQT, anybody remember what that is? Water quenched in temperature. Right. Good job. Compute the resulting design factor for this design. All right, the section given looks like this. 3 inches on this side, 2 inches on this side. Okay, what is the condition on either end of the rod? Fixed pinned. Okay. Now the length of the rod looks like it's 12 3/4 feet. Let's go ahead and calculate the effective length. Let's see. So let's go back in the chapter. Have a page number in a moment for you. Yeah, 607. If we have a fixed pinned column, then the effective length is equal to only 80% of the length. Now in our case, the length was 12 3/4 feet. So somebody take 80% of that if you would, please. I'll try to do it in my head in the meantime.
2.2.
Can't be 2.2.
10.2.
Oh, 10.2, okay. Thank you. So 10.2 feet. How about the slenderness ratio? Because that will be required anyway. Well, that's the effective length divided by the radius of gyration. The radius of gyration would be the square root of I over A. So now we have a choice. Which axis do we want? IX or IY? IY, right? Because that's the way that it's going to buckle. So if we want to calculate IY, which is the minimum area moment of inertia, how would we do that? It's a rectangle, 1/12 BH cubed. So 1/12, well, which one are we going to use as the base?
HB cubed.
HB cubed, if we make this H and this B, right? So we're going to make we don't want to cube this because that'll make I as big as possible, right? We want to cube this one. Okay, so 2 inches cubed over 12. Okay, times 2 is 4, times 2 is 8. 8 times 3 is 24. 24 by 12 is 2. So if I did all the math right in my head, then that's 2 inches to the 4th power. Now the amount of area, A, would be 6 square inches because 3 times 2 is 6. So to calculate the radius of gyration, we just have 2 inches to the 4th divided by 6 inches squared. So I need you to take your calculator and take the root of 1/3. I don't know what that number would be.
0.573.
0.573. Anyone second that? All right. So now we can calculate the slenderness ratio. 10.2 divided by 0.573. Nobody's going to stop me? Be really careful. You always have to know what units you're using, okay? Let's add in 12 inches per 1 foot. You guys just thought I knew what I was doing, right? We trust you. Go ahead. Okay, anyone have a slenderness ratio number for me?
213.6.
13.6. What are the units?
Non-dimensional.
Non-dimensional. That's right. That's why we write ND after it. Okay. So there's our slenderness ratio. All right, go to page 609, please. We're going to calculate the, we're going to call it the column constant. Basically a critical number. It's the root of 2 pi squared E over SY. And so you see we're going to have to go look up the properties of this metal. I should have written down what metal we were using. Go to the problem statement and find it again. 22, it is 1040 WQT 1100. Don't think we need this anymore. But we do need some material properties. So if we go to page 714, we should be able to find this. Yeah, here it is. It's down a little bit, but near the top. What all do we need? Well, we need the yield strength for sure. And the yield strength looks like is 80 KSI. As well, we need the elastic modulus, but this is the table that recommends 30 times 10 to the 6th PSI for the elastic modulus. Okay? So now let's calculate the column constant. Root 2 pi squared, the elastic modulus, 30 E6, divided by the yield strength, 80 E6. Notice both of these are PSI, so I didn't bother writing it down. That way we don't have to deal with E6. You could even cancel a 10 if you wanted to. So 6/8 are a quarter. So quarter times pi squared square root is how much? Basically, it's pi times root of a quarter, or 3/4. So what's our column constant? It's going to be the same thing as pi root 0.75 if I did that right. Have a number? Did I do something wrong?
Should it be 80 E6 or 80 E3 with the PSI?
You're right, thank you. 80 E3. It's going to make a difference. So in that case, this needs 1,000, so how about 750? Thank you.
At 86.04.
Thank you. 86.04, and that is also non-dimensional. Now, let's see. If the, just below on page 609, below equation 11.3, if the actual effective slenderness ratio is greater than CC, yeah it is, and the column is long, and the Euler formula should be used. So we need to go use the Euler formula. So let's go do that. All right, page 611, equation 11.4. For long columns have an effective slenderness ratio greater than the transition value, the Euler formula can be used to predict the critical load. So there's the formula. There's two versions of it. 11.4 and 11.5 are the same thing. You may want to make a note of that. Your author has both. Just make a note that says use whichever one's easiest. Okay? Which one do you think would be easiest for us to use, 11.4 or 11.5? I personally like 11.5 because I can't remember what the radius of gyration was. Okay? I think we can figure out the area moment of inertia I pretty quickly and easily. In fact, I think it was 2 inches to the 4th, wasn't it? So the critical load then, and this is because the slenderness ratio is greater than the critical value, then the critical load is pi squared EA, let's try EI, I'm trying to use 11.5, not 4, effective length squared. So let's see, that would be pi squared 30E6 PSI multiplied by 2 inches to the 4th divided by the effective length, which was 10.2 feet. We'll go ahead and multiply 12 inches per foot before we take the square. So we just convert the units to inches, and that should give us the critical load. Okay, so please take your calculator. Notice what will happen. We'll have inches squared in the denominator down here. There will be effectively inches squared in the numerator once we put those together. Inches squared in the denominator of PSI, so we'll end up with pounds. Okay, so this is pounds force. How many pounds force can this rod take? So this is 30 times 10 to the 6th. $39.52.6.
I got 39,526.
Me too.
Okay. I was going to say this thing fails quickly if it's, if it's really that. Okay. You may not have had that 0 in there or something.
I did 3.0 times.
Yeah, that's fine. Okay, thank you. All right, so 39,000 or so. The load was what, 12,500? So the factor of safety N would be the actual, or the critical load divided by the actual load. We usually use A for allowable, so I won't write that down. So the critical load, 39,526 pounds force divided by the actual applied load of 12,500 pounds force. It's a factor of safety of about 3 or so. What's the actual number? 3 point something.
3.16.
And that's non-dimensional, of course. This is a factor of safety of about 3. Any questions on that problem?